Hello, good morning, student. How are you? I hope you all are happy, healthy, and fine at home. What did we discuss yesterday? Yesterday, we discussed about the ozonolysis, formation of aldehyde and the ketone. So, what are the reagents used there? How the ozone molecule, what are the resonating structure of with the suitable example, and why it is used for the determination of the structure of the unknown compound. That type of the analysis we have discussed yesterday. What we are going to that, as well as we summarized all the reaction together on by taking the suitable starting substrate, which is propylene, and we carried out all the reaction under one heading, and we discuss that collectively. So what we are going to learn today we are going to learn about the reaction of carbon-carbon triple bond, because we are studying the chapter number 4. The name of that chapter, reaction of unsaturated hydrocarbons and carbon oxygen double bond. In that, so far we have learned reaction related to carbon-carbon double bond, and now we are discussing the reaction related to carbon-carbon triple bond. And as we know that triple bond is formed, there is a one sigma bond, and as we know that sigma bond are formed due to the coaxial overlapping. That sigma bond is there. In addition to this sigma bond, there are two bond which is known as pi bond, and pi bond are formed due to the lateral overlapping of the p orbital, or there is a sidewise overlap to form as a pi bond. So here middle one we can call it as a sigma bond, and these two are pi bond. And as we know that when the number of pi bond increases, means pi bond is nothing but as a pi electron involved there, and number of pi electron present over there, it act as a nucleophilic in nature, and similar to the alkene, carbon-carbon triple bond, that is known as alkyne, which is just shows the similar reaction with that alkene, right? And that undergoes electrophilic addition reaction. The reaction like addition of hydrogen, addition of halogen, addition of hydrogen halide. But here remember, here in a carbon-carbon double bond only one equivalent of the molecule get consumed, but in this case there are two double bonds are there, and therefore two moles or two equivalent moles of reagent consumed, and resulting into as a product, means 2 mole get consumed by that triple bond, and we are getting as a saturated compound. Formation of that product shows the sp3 hybridization, that is a saturated compound. In addition to this, or beside to these reactions, the terminal alkyne shows displacement reaction. Displacement reaction is nothing but as a substitution reaction due to the more acidic hydrogen atom present in triply bonded carbon, and that carbon atom is a highly acidic in nature. Why it is a highly acidic in nature? That terminal alkyne, that proton attached to that carbon atom is a sp hybridization, and when sp hybridization is there, that hydrogen atom held by that sp hybridization, the nucleus of that carbon-carbon triple bond is tightly, means the shortest bond length are there, and therefore that hydrogen atom is more acidic in nature. And when it is more acidic in nature, it provides best, or what we can call it as a excellent synthetic route to form the organometallic compound. That is a speciality of this compound, and such reaction provide the best route to the important organometallic compound, and therefore that's why the reaction of this carbon-carbon triple bond is a very, very important as far as a synthetic point of view is concerned. We can form the new carbon-carbon bond. When the new carbon-carbon bond is formed, there is a generation of the new organic compound, and which is useful as far as a chemist point of view is concerned. So that is the speciality of this compound. For example, suppose we have this is what we can call it as a general introduction regarding as a carbon-carbon triple bond. And now here, as we know that suppose is R C triple bond C and H. This proton is a highly acidic in nature because it is attached to the carbon atom which is a sp hybridization, and due to this it is a highly acidic in nature. If you compare with that alkene or the alkyne, it is a highly acidic in nature, and that molecule becomes as a cylindrical in nature. In case of the carbon-carbon double bond we have seen here, in case of this hydrogen atom and this double bond, there is the electron density present on this alkene is above the plane as well as below the plane. This is a pi electron, this is a pi electron. The electron density distributed or spread over this and there. But in case of the acetylene molecule, what is happening? The electron density, this the acetylic proton, the electron density, it is just like as a cylindrical one. This type of here is a carbon atom, and this is a cylindrical type of the electron density over there, and this is a deprotected, means this proton is a highly acidic one, and this is a cylindrical distribution of that electron cloud over this, and that's why it is a highly acidic in nature. And if you treat this compound in presence of any what we can call it as a, let us see, suppose as a Grignard's reagent, we know that RMGX, Grignard's reagent, everybody knows that the Grignard's reagent RMGX, how it is prepared? It is prepared from the alkyl halide. Pure alkyl halide treated with pure magnesium metal in presence of ether, resulting complex form is a RMGX, is known as a Grignard's reagent. And Grignard is a scientist name. He received the Nobel Prize for the simplest reaction what he did, because if you remember here Rx is plus delta charge minus delta charge over there. When the metal group is inserted, this is organometallic type of the compounds are there. Now the nature of R is exactly opposite to this alkyl, and if you remember the organic compound, most near about 75% of the organic compound containing as a carbonyl group, and carbonyl carbon is a electrophilic in nature, and therefore this type of the nucleophile easily attack on that carbonyl carbon, and there is a formation of the carbon-carbon new bond, and therefore we can prepare the 1,000 or million of the organic compound by using that reagent. And that's why this is a utility, or what we can call it as a application of that Grignard's reagent. So we can prepare primary alcohol, secondary alcohol, or the tertiary alcohol. But if you treat with this is a highly acidic, it will pick up the proton over here, and you are going to get R, then C triple bond C, then MgBr, and plus here is a RH, means alkane you are getting. Side product is alkane, that is in a gaseous form that goes in the atmosphere. So this is a acetylide formation take place over here. And if you further treated with suppose as alkyl halide, what do you get? R, C triple bond C, and then R plus MgBr X, you can call it. This type of the alkyne, higher alkyne you can prepare by using as a this type of the things are there. So this is all about the introduction regarding the carbon-carbon triple bond. So now let us move on to the reaction, general reaction. What are the general reaction we are going to see in this particular chapter? So let us see. First one is the addition of hydrogen. As we know that first one simply is the addition of hydrogen. Addition of hydrogen, and as we know that molecular hydrogen is added across the carbon-carbon double bond or across the carbon-carbon triple bond. The saturated compound becomes as unsaturated, but for this there is a catalysis is required, and as we know that the function of catalyst to lower the activation of energy with the help of energy profile diagram. While studying the reaction of carbon-carbon double bond, we already learned, and these kind of the reaction are exothermic reaction. Why the exothermic reaction means there is a bond breaking takes place in that. Now this H2 generally H2 is added in presence of the catalyst like as a platinum, nickel, or palladium, ruthenium, or rhodium. These type of the different catalysis we can use along with the molecular hydrogen, and we will get the different type of the we will get the formation of the alkyl. Let us see here one more example. The example we are taking here, the simplest alkyne, suppose we have this one CH3, then C triple bond C, H is there, right? Or let us, this is a one propyl that will be treated with H2 in presence of nickel. Now here the 2 moles of H2 is required because there are the 2 pi bonds are there, and therefore 2 moles of hydrogen molecule is required to convert that compound into as a this one. We will get CH3, CH2 and the CH3. That type of the product formed here, which is known as a propane, right? Everybody knows that. Suppose what will be the RUHC name of this compound? You can number from this side 1, 2 and 3 because this carbon-carbon triple bond is there, so it is there is a terminal hydrogen atoms are present over there. Now let us look at the name of this compound will be propyne. Last suffix is a YNE that indicate as a, suppose the organic compound contain as a carbon-carbon single bond, there will be a last suffix ANE. Carbon-carbon double bond, last suffix should be ENE. Carbon-carbon triple bond, last suffix is a YNE. These are the suffix or the ending word you have to put there while writing. Prop indicate as a 3 carbon atom in the straight chain, and YNE indicate there are the 3 carbon-carbon triple bonds are there, and that's why it is a RUHC name of this compound. Now let us one more example here, CH3, C triple bond C and the CH3. One more example is there. The name of this compound is a 2-butyne. 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 YNE, butyne, but indicate as a 4 carbon atom in the straight chain. 1, 2, 3 and 4. 4 carbon atom in the straight chain, and at a 2 position there is a carbon-carbon triple bond. Therefore, these 2 indicate as a position of the carbon-carbon triple bond, but indicate as a there are 4 carbon atom in the straight chain. YNE indicate as there is a carbon-carbon triple bonds are there, and that's why it is there. Now it will be treated with 2 moles of H2 in presence of nickel or platinum. What do you get? The 2 moles get consumed due to the presence of carbon-carbon double bond in the starting material or in the substrate, and we are going to get the product CH3, CH2, CH2 and CH3. This is a N-butane. It is known as N-butane. Last suffix, look at here, ANE means this organic compound containing carbon-carbon single bond. N indicate as a normal. Normal is there. Normal straight chain is there, and that's why it is called as a N-butane. Normal. N stand for the normal, N-butane, and as we know that zigzag way we can write that one. Let us this N-butane over here. But this carbon-carbon triple bond we can by using as a special condition, by using the proper reaction condition, we can control the reaction at alkene stage only. And the proper condition, what are those proper conditions? Let us see here. Suppose this compound, same compound, suppose treated with, it is a very important as far as exam point of view is concerned, or what we can call it as a competitive exam point of view is concerned. Suppose let us see here, we have this one middle one, CH3, C triple bond C and CH3. The name of this compound, as we know that just now we have seen 2-butane, right? 2-butyne, it is a starting compound, let us see here. And now if this is a treated with, we are controlling this reaction that H2 in presence of palladium, hydrogen oxide in presence of palladium, and barium sulfate SO4 or barium carbonate, you can remember, that are the bases or supporting is used, and this reagent is known as a Lindlar catalyst. Lindlar catalyst. This is known as a Lindlar catalyst. Lindlar is a scientist name. He invented this first time, and therefore name is given to that catalyst, which is known as a Lindlar catalyst. And this catalyst specifically prepared in the palladium, and what is happening, it gives the product is a cis product, carbon-carbon double bond. As we know that cis product, stereochemistry here involved is a very important one here. Look at the methyl group, one methyl group over here, another methyl group over there. Similar group are on the same side of the carbon-carbon double bond is known as a cis isomer, and the name of this compound is a cis 2-butene. We control this at a we kept the special condition here, that is a Lindlar catalyst, and we are getting as a this type of the cis 2-butene starting from the 2-butyne. And if you treat this same compound with the Birch reduction, that is known as a you can use as a sodium metal in presence of liquor ammonia NH3. Sometimes it is written as sodium in presence of liquor ammonia, this one, or it is written as NH2. NH2 is nothing but as a sodium amide. This is known as a sodium amide, and which is a very strong base, and this is obtained by dissolving the sodium metal in liquid ammonia. And what is happening there? The reaction is exactly opposite to the Lindlar catalyst. Whatever Lindlar catalyst gives the specifically selectively cis-2-butene, whereas this Birch reduction gives the reaction exactly opposite. Exactly opposite means here is a cis isomer we are getting. Now here what we are going to get? You are going to get as a trans, same thing, but here must be as a trans 2-butene you are going to get. Trans 2-butene. Trans 2-butene, because here let us see, here is a carbon-carbon double bond. I am writing one methyl group over here, another methyl group must be here, hydrogen atom here, and this hydrogen atom. Look at, observe this reaction carefully, observe this product. What do you see? This methyl group and this methyl group, they are identical, but they are opposite to the carbon-carbon double bond, and therefore this type of the isomer is known as a trans isomer. Trans isomer, again statement about that trans isomer means what? The similar group are on the opposite side of the carbon-carbon double bond is termed as trans isomer, and this is a trans 2-butene. This is a very, very important as far as your exam point of view is concerned, or you are going to appear for the competitive exams. This type of the selective reactions are frequently appear in the competitive exam. So remember why we are getting as a this what is the name reaction. Sometimes only as this type of the reagents are reagent, but you have to mention the scientist name also. This is a Lindlar catalyst. Lindlar catalyst. Sometimes it is not given, only written on the arrow is a Lindlar catalyst. You predict the product. What? The predict the product here. Just remember, mechanism is not at this level. Mechanism for MSc level, that time we will see. But here just remember as a this. If you add as a Lindlar catalyst gives the cis-2-butene, where if you use as a this one is a Birch reduction, it gives the trans 2-butene. This reaction is known as a Birch reduction. Birch reduction, and this is a Lindlar catalyst. I think this is a reaction. Now let us look at as a second reaction, addition of X2 reaction. Second one is a addition of halogens. Addition of halogens. Second reaction is a addition of halogens. Second reaction is a addition of halogens. Second one, addition of halogens. Halogens. Halogens means here X2, right? Reaction of halogens. Now these halogens can be treated with the inert solvent like as a carbon tetrachloride, and we are going to get here, simply we are going to consider here the reaction like this. Suppose let us see, starting compound CH3, C triple bond CH, that is a propyne, as we know that the name of this compound is a propyne, and that will be treated with here 2 moles of Br2 in presence of CCl4. What do you get? You are going to get the product is this one CH3, then Br, then BrH and Br. The name of this compound is a you start from this side 1, 2, 3. Why that side numbering? Why I am giving a numbering from this side? Because look at the halogen atom, they are present at the terminal carbon atom, and therefore you should start the numbering from the right hand side. That is a right thing to number this. Now what will be the RUHC name of this compound? Look at one position. So 1 indicate as a position of this bromine atom. Again at 2 position there will be a 2 bromine. So total become as a 4. If 2 is there, we are calling as a di. 3 is there, we are calling as a tri. 4 is there, we are calling as a tetra, and therefore you can call it as a tetra, what is that? Bromo, tetra bromopropane, tetra bromopropane, that is the RUHC name of this compound. Look at this one. This is about the addition of halogens. Now let us look at as a third general reaction we are here. Addition of hydrogen halides. Addition of hydrogen halides. Addition of hydrogen halides means HX, right? Addition of hydrogen halide is nothing but as a HX. And when the addition of hydrogen halide, let us see same unsymmetric alkyne, carbon-carbon triple bond, hydrogen atom present at terminal 1, that is what do we can call it here? The name of this compound is propyne, right? Propyne. And now when we are adding HX, mechanism we will see later on. Here we just finding the general reaction. Here again as a 2 moles of hydrogen halides are get consumed and the product is formed here. Now it's a CS3, CX, then CS3. Look at here, what is happening? The halogen atom, they are the addition reaction again follows as a Markovnikov's rule in this case. And what the Markovnikov's rule tells us that in an addition reaction, negative part of the reagent attached to those carbon atom which carries less number of hydrogen atom, and these halide, 2 halide group are present on the same carbon atom. This type of the position is called as a geminal halide. This is called as a geminal halide. Geminal, and previously we know that vicinal, right? Vicinal means what? They are present at adjacent carbon atom 1, 2 or 1, 4 position. Geminal means 1, 3, or we can call it as the same halogen or whatever same or functional group. 2 functional group are present on the same carbon atom. That position always termed as a geminal position, and if both the 2 halide group they are present at adjacent one, that is known as a that type of the position is known as a vicinal. And why we get this one, that we will see later on while studying as a mechanism of this reaction. Now let us look at as a fourth reaction, addition of water. Fourth one, addition of water. Fourth reaction we are learning here. Fourth reaction, addition of water, which is known as a hydration reaction. Now suppose we have a starting compound is this one. Let us see CS3, C triple bond C H is there, and that is treated with water H2O in presence of H2SO4 and HgSO4, mercury sulfate, and this, what do you get? You are going to get the formation of compound is the C double bond O CS3. How we are getting this acetone? While studying as a mechanism, we will see the detail of that. Why we are getting as a such type of the thing while adding as a what? Suppose you have this type of the compound, triple bond CH. This is a propyne, you know that, right? Propyne, and this is known as acetylene molecule. Acetylene molecule, when treated with the same reagent H2O in presence of H2SO4 and HgSO4, what does it give? It give the acetaldehyde, C double bond OH, carbonyl group are there. Here we are getting as acetaldehyde, but here we are getting as a acetone. Again the reaction are carried out according to as a Markovnikov's rule. And Markovnikov's rule tells us that in an addition reaction, negative part of the reagent attached to those carbon which carries a less number of hydrogen atom. And this is all about the reaction. Now let us look at the next reaction, formation of the metal acetylides. Formation of metal, fifth reaction, formation of the acetylide. It is one more, fifth reaction, formation of acetanide. Formation of acetanilide. Formation of acetanilide. Formation of acetylides. Formation of acetylides. Formation of acetylides. Formation of acetylide. Look at the word formation of the acetylides. What are the reagents generally used here? One is a lithium amide, or what we can here, suppose we have this one, CH3, then C triple bond C, the terminal alkynes are present, then and then that type of the acetylide things are happening, that will be treated with lithium amide NH2, it gives here CH3, C triple bond C Li, that is lithium methyl acetylide. This is a lithium methyl acetylide, lithium methyl acetylide. Or if you treat with this reagent, that is a sodium amide NH2, it gives this one CH3, C triple bond C Na. Here is a positive charge, negative charge, here is a positive, here is a negative, that is called as a here is a sodium methyl acetylide, or you can use here the Grignard's reagent, as we know that CH3 MgBr, and we are going to get here this one CH3 C triple bond C, then MgBr, that is which is ethylene magnesium bromide, or the methyl magnesium acetylide, magnesium bromide here, ethylenic or propynylic methyl bromide, and here the side product obtained will be this one, that is a CH4 methane molecules are obtained over here. So these are the some of the general reaction we have seen here. So tomorrow we will see the mechanism of electrophilic addition to carbon-carbon triple bond, how the mechanism, with the help of that we will discuss all these main 5 reactions regarding the carbon-carbon triple bond. I think let us stop today here, remaining we will see the next time. Have a nice day. Thank you.